In this video, we're going to write some code that tests whether or not we need to check for our initial rotation values increasing or decreasing. What I mean by that is we start off by assuming an initial value of rotation, right? Now, that's almost certainly not going to be the correct value of rotation. In our case, that's the rotation at support A. And so we're going to need to either increment it in the positive direction or increment it in the negative direction, increase it or decrease it basically. So what we want to do in this video is write the code that tests and tells us whether or not we need to be increasing our initial guess for the rotation or decreasing our initial guess for the rotation. So that's the task at hand. So you'll notice here that I have a new heading, test whether we need to sweep for initial rotation values in the positive or negative direction and call the sweeper function. Okay, so you notice that this is 5.5 and the last heading was 5.3. So in the next video, we're going to come back and write the code for 5.4 essentially, which is a function that's going to solve for the correct initial value of rotation. All we're doing in this lecture is working out whether we need to be testing in the positive, i.e. adding to that initial guess, or taking away from that initial guess. Right, so let's just get into it here. So the first thing that I'm going to do is give myself a heading. So we're going to test whether reducing or increasing the initial rotation leads to a reduction in the displacement error at the other support, and for us that's support B. Okay, so what we're going to do here is we're going to call our deflection function and we're going to calculate the deflection for our beam with 3 different values of the initial rotation. Remember, we defined initial rotation. Let me see. We defined this guy here. This was the initial rotation. We're going to create 3 values. One is going to be the initial rotation minus delta rotation. The second value is just going to be the initial rotation, and then the third value is going to be the initial rotation plus delta rotation. Okay, and then we're going to calculate the deflection for each of those 3 guesses for the initial rotation, and we're then going to test which direction or which one leads to a smaller value of the deflection at B, which remember should be 0 because that's a support. So let's start off by defining an array of zeros again. So I'll say test deflection, right, is going to be equal to np dot zeros, and it's going to take 3 values, right? Just going to be an array of 3 zeros initially. And we're going to overwrite each of those values with the different values of the deflection at support B that we calculate based on our 3 different initial guesses. All right then, so let's do a little loop. We'll say for I and or in enumerate. Now, I want to cycle through 3 possible initial rotation values. The first one, as I said, was going to be whatever the initial rotation was minus the delta rotation. The second value that we're going to run this code for is going to be just the initial rotation on its own, and the third value is going to be the initial rotation plus delta rotation. So you can see what we're doing here. We're going to check and see whether reducing our initial rotation leads to a smaller value of deflection at support B, or whether increasing our initial guess leads to a smaller value of deflection at support B. So that's our for loop setup. Let's just call our function our calc deflection. That was the function we defined in the last lecture, and remember, we got to pass it in some information. We got to tell it what are the moment values, what's the flexural rigidity, what's del x, what is or. Well, or is the initial rotation. It's going to be one of the values within this array of 3 values, and or is the current value for the current iteration of the loop. And then we're going to pass in the initial rotation, or rather the initial deflection I should say, and we define that as initial deflection. It's going to be 0 at support A. Right, we're going to assign the output. Remember, that function gives us back a rotation and deflection array. Let's just define those 2 new variables. We'll reuse the names rotation and deflection because we're outside the scope of that function now. So rotation and deflection. And now let's just assign whatever value we have for the deflection at support B into our test deflection array. Right, so what is that? We're going to say, let's start off by saying deflection. Now, which value of deflection do I want? I want the value that is at location support index B. Remember, I can't necessarily take the last value because we might have an overhang to the right, and in this case we do have an overhang, a cantilever overhang to the right of support B, and that's why I can't take the very last value in all of these in this array of deflection values. I need to take this specific value. All right, okay, and we're going to assign that into test deflection. Where are we assigning it? Well, we just put it into the first slot. Okay, so that is going to give us all of our different test values for the deflection at support B. Now what we need to do is ask ourselves the question, does that deflection at support B, does it get bigger or smaller when we increase or decrease the initial rotation value for A? So again, some simple logic is going to test this for us. We'll say if the absolute value, right, we're only interested in the absolute value of test deflection, okay, test deflection at position 0, so the first value, if that first value, which we obtained by reducing our initial rotation, right, so if that is less than the absolute value of test deflection at position 1, right, if that's the case, okay, so in other words, let's sort of follow the logic here. So if the value I obtained by passing in this initial guess, if that happens to be smaller, i.e. the deflection at B happens to be smaller than when I passed in this initial rotation, well, that means reducing, right, that means reducing the initial guess for rotation is leading to a smaller error, and we want to continue reducing the initial rotation in order to further reduce that error. So let's just capture that in a note, right? So we need to test in, I'm calling it the negative rotation direction, by reducing the initial rotation guess, and that's the basic logic. Let's do a print statement here. So we need to test in the negative direction, I'm going to say. So we won't worry about what happens next for now. Let's just implement the second check. So if that was the case, that's fine. We need to test in the negative direction. Else if we need to test the opposite, right? So else if I'll say absolute value of test deflection 2, so that was a deflection for support B that we obtained when we passed in this initial rotation. So if that happens to be less than the absolute value of the deflection at B that we obtained, let me see, at location 1. So that was the value of the deflection at B we obtained when we passed in this value for the initial rotation. So if that's the case, well, then we need to test in the positive direction, because what we're saying here is increasing the initial guess for the rotation at A is leading to a smaller error. Okay, and so we need to further reduce that error by testing larger and larger values of the initial rotation. So let's just, for clarity, give ourselves a print statement here. All right, so that's quite a lot done there, right? We've implemented quite a bit of logic there, but we haven't actually done anything other than generate a print statement when we've identified the correct direction in which to test. So we need to do something, right? So we need to calculate what is the initial rotation, right? What would the actual value be? We know which direction we're testing in. We're either increasing that initial rotation to reduce the error, or we're decreasing the initial rotation to reduce the error. And so what we now want to do is we want to call another function, which we'll write in the next lecture, but we'll call it now. So we'll say, we're going to call it zero crossing. You'll see why in the next lecture. But zero crossing, this function is going to take the deflection. It's going to take what is the delta, the amount by which we're changing our initial rotation. And remember, in this case, we are reducing that guess, and so our delta is going to be a negative delta rotation. It's going to take that information as well. It's going to take the initial rotation, and it's going to take the initial deflection. Right, so our function, which we don't know anything about yet because we haven't written it, we're just calling it, we're going to imagine that gives us the correct value, or the solved value of the initial rotation. So we'll assume that this magical function, which has yet to be written, it's going to take in that information, and it's going to do all of the magic that ultimately ends up identifying the correct value of the initial rotation. So that's all we need to worry about for this lecture, right? Don't think about that anymore now until the next lecture. Now, on the other hand, if we need to test in the positive direction and start increasing our initial guess, well then we can call the exact same function. It's just that we're going to pass in a positive value of delta rotation, and that will return the correct value of the solved initial rotation. All right, so at this point in time, right, we've worked out what the actual correct value, or the closest we can get to the correct value of initial rotation. All we have to do now is actually finally run our deflection calculation function and pass in the correct value of the initial rotation. Right, so let's say we're going to say rotation and deflection is going to equal to calc deflection this time. So this is the final run of our calculation deflection, or deflection calculation. And what are we going to pass into this, right? We're going to pass in all of our moment values again. Our EI values haven't changed. Our delta x hasn't changed. But what has changed is we can now pass in the correct value, or as close as we can get it, to the initial rotation, and we can pass in the initial deflection, which would remain unchanged at 0. Excellent. And so that deflection that gets returned is going to be our best approximation of the actual deflection for this beam. So now I'm going to, just for the purposes of demonstration, I'll generate a couple of print statements. So the first one is going to be, I want to print out what was the solved value of the initial rotation, right? So I'll just use a print statement, and I'll call format on the end of it. So I'll say the solved initial rotation is 1 as a variable, and then in calling format, I'll assign 1 to be equal to the solved initial rotation, give us a nice print statement. And then I'm going to have another print statement, and I'm going to print out what is the actual error. So even though I've gotten the closest possible value that I can get with my numerical approximation to the correct value of the initial rotation, there's likely to still be some error, right? So what is that error, right? So the error, i.e. the residual displacement at support B, you can think about it that way. The error in displacement at support B is, again, 1 as a variable, and this time I'm just going to assign 1 as the value that I obtain from reaching into that array of deflections, that's this guy here, and pulling out the value at that corresponds to the deflection at support B. All right, and that is it. That's all we wanted to do in this lecture. So again, it wasn't too hectic, but a little bit of logic to wrap your mind around there. The first thing we did was calculate 3 possible deflections for the deflection at support B. One obtained from the initial rotation itself, one obtained by reducing the initial rotation, and one obtained by increasing the initial rotation. And that allowed us to identify whether increasing or reducing that initial rotation guess value led to a larger or smaller error. Once we worked out whether we needed to be increasing or decreasing our initial guess, well then we could go ahead and we could call a function that would solve for the initial rotation at support A. And that function would either, well, we haven't written it yet, but that function would either start reducing that initial rotation and keep testing and testing and testing until we get to the smallest possible value of the deflection at support B, or it would increase our initial rotation guess incrementally until we achieved the smallest possible deflection at support B. All right, so take a break for now, and we'll come back in the next video, and we're going to actually write this zero crossing function that's going to solve for the correct, or our best approximation for that initial rotation at support A. Okay, we'll pick it up in the next one.